Hello and welcome to our video presentation. Today we'll be presenting on the topic ultrasound wave in underwater imaging. So sit back and enjoy the presentation. Let's get started. My name is Roberto Maisara and this is my group teammate. We have Adriana Sara, Masra Hazira, and Idina Hani. Hi everyone, I will be introducing you to the fascinating world of ultrasound wave and their role in underwater imaging. Let's start with what ultrasound is and why it's so powerful beneath the surface. Ultrasound refers to sound wave with frequency above 20,000 Hz, far beyond what we can hear. These high frequency waves are especially useful in environments where light cannot travel effectively like underwater. So next, what is underwater imaging? Underwater imaging, also known as sonar imaging, use ultrasonic waves, which are high-frequency sound waves, to create picture of object and environment beneath the water. It's very similar to how bats use echolocation to see in the dark. The sound waves are sent out, and when they hit something like the ocean floor or an object, they bounce back. These returning signals are then analyzed to build a visual image. This technology helps in mapping the seafloor, detecting underwater objects like shipwreck or submarine, and even observing marine life in their natural environment. So, why ultrasound is very important for underwater imaging? This is because ultrasound imaging play a crucial role underwater because light simply can't go very far. In contrast, sound wave can travel much farther and faster in water. This makes ultrasound ideal for deep sea exploration, detecting shipwreck, inspecting or pipeline, and even studying marine animals. It's safe and reliable method to see underwater where our eye can't. One reason ultrasound is so effective underwater is because sound travels over 4 times faster in water than in air, around 1,500 meters per second. This is due to the density and bonding of water molecules, which helps sound waves move more quickly. But that speed can also change depending on the water temperature, pressure, and how salty is it. This factor must be considered in underwater imaging system to ensure accurate reading. Since ultrasound waves are reflected by object, we can use the returning angles to calculate distance and even form image of the sea floor or underwater structure. For example, sonar system in submarine calculate how long it takes for the sound wave to hit an object and bounce back. Using the known speed of sound in water, they estimate the distance, even the shape of the object.
Hi everyone, in this slide I'll be explaining how ultrasound is used in imaging. Ultrasound is widely used for underwater imaging through a technique called sonar, which stands for sound navigation and ranging. Here how it works. A sonar system sends out ultrasound waves, usually between 20 kHz to several megahertz into the water. When this wave hits an object like the seafloor or a submerged structure, they bounce back to the source. By analyzing the reflected wave, we can create an image of the object or understand its position and shape. This technique is especially useful in underwater exploration and mapping. Now, let's explore the key instruments involved in sonar technology. First, we have the transducers. These are essential devices that convert electrical signals into ultrasound waves and back again using something called the piezoelectric effect. This process is what allows sonar system to both send and receive sound signals underwater. Next, we have the transmitter. And it sends electrical energy to the transducers and helping it produce high frequency sound pulse. These signals also typically range from 20 kilohertz to several megahertz, and the transmitter ensures the pulse are strong enough to travel long distance underwater, making sonar effective even in deep or murky environments. Continuing with the key instrument in sonar, let's talk about the receiver and the processor or display unit. The receiver captures the ultrasound echoes that return after bouncing off objects. These echoes are sent through the transducers, which converts them back into electrical signals using the piezoelectric effect. The receiver also boosts the signal and remove noise before passing it to the processor. By measuring how long the echoes take to return, it also helps to calculate the distance of the object. Next is the processor or display unit. This component turns the echo signal into image. It calculates how far object and where are they located based on time delays. It also reduces noise, process all the data, and finally display 2D or even 3D image on the screen. This step is all about turning sound into something we can see and understand. Next, let's move to diagram sonar system and wave operation. This diagram shows the basic operation of a sonar system. It starts with the transmitter, which sends electrical signals to the transducer, and then the transducer converts these signals into sound wave that travel through the water. And this sound wave, called transmitted wave, move outward until they hit a target like the seafloor or an object underwater. The waves then bounce back as echoes. The returning echoes are picked up by the receiver, which sends the signal to the display unit, and finally, the observer views the visual output on the screen, and the entire process allows us to detect objects and measure distance underwater using sound wave.
Next is application of ultrasound wave underwater imaging. So the first one is seafloor mapping. Ultrasound or sonar is used to send sound wave to the ocean floor. The time it takes for the echo to return helps create a detailed 3D map of the seabed, including its depth, shape, and features. This is essential for marine research construction, like laying pipelines and navigation. Next is submarine navigation. Submarines use ultrasound to detect underwater obstacles, terrain, and other vessels. It allows safe travel in areas with no light and where GPS does not work. For number three, fish detection. Fishermen and researchers use ultrasound to locate schools of fish. Fish Fish finders send ultrasound pulse and detect echoes from fish bodies, which helps determine their size, depth, and movement. For underwater archaeology, ultrasounds helps identify buried or hidden objects like shipwrecks, ruins, or debris under layers of mud or sand. It helps archaeologists study submerged historical sites without disturbing the environment. For the benefits, the first one is work in dark or cloudy water. Unlike cameras, ultrasound imaging does not rely on light. This makes it ideal in deep ocean areas or turbid water where vision is limited. For non-invasive, ultrasound does not harm marine animals or the underwater ecosystem. It is a passive click method of exploration. Real-time imaging. The technology provides instant feedback. For example, submarines can avoid collision in real time, and researchers can monitor fish as they swim. Last, deep penetration. Ultrasound can go deeper than light or video, even through sediment or underwater structures, and is revealing what is hidden from the human eye. So, despite of the benefits, there are some challenges that you need to face. So the first one is signal loss over distance. As ultrasound waves travel further in water, especially in salty or deep water, they lose energy. This reduces the range and clarity of imaging. Second, resolution versus distance. High frequency ultrasound give better details, which is resolution, but cannot travel far. Low frequency travels further but produce blurrier images. A balance must be found depending on the use. For number three, affected by environment. The speed and direction of ultrasound wave can be affected by water temperature, salinity, and pressure. These variables must be measured and correct during processing. 4. Complex data processing. Raw ultrasound is not directly readable. It must be processed using algorithms and software to generate meaningful images or data. This can be expensive and requires technical expertise.
Hi, so next I'm going to explain about the future developments and innovation. The first innovation is biomimetic sonar technology. This technology is inspired by dolphins and whales, which naturally use echolocations to navigate and hunt underwater. By mimicking their echolocations, future ultrasound systems can adjust their sound signals automatically depending on the water conditions. This adaptive sound control allows them to work effectively even in challenging environments like murky water or areas with a lot of obstacles. With this, they can detect objects more accurately, which is really helpful for underwater explorations and rescue operations. The next innovation is the integration of artificial intelligence or AI. AI helps the ultrasound system by reducing background noise in real time, making the image much clearer. It can also detect objects automatically, whether it's marine animals, underwater cables, or damaged structures. What makes AI even more powerful is its ability to learn and improve over time, becoming more accurate the more it used. This also can reduce human error and save a lot of time during analysis, which is very useful for underwater monitoring or inspection. The third innovation is focused on high resolution and deep sea imaging. This technology combines high frequency and low frequency ultrasound. High frequency provides clearer image while low frequency allows deeper scanning. By combining both, it can produce clearer image even in deeper or murky waters. This technology is suitable for ocean mapping and marine studies, where both details and depth are important. It also very useful for industry like oil and gas, where accurate underwater imaging is necessary for safety and maintenance. So, in conclusion, ultrasound waves are ideal for underwater imaging because they travel better in water than light. That's why sonar is used to detect and map underwater areas, especially in deep or murky conditions. This system is based on physics concepts like wave behavior, sound speed in water, and the piezoelectric effects. Instruments such as transducer and processors work together to convert sound waves into image. It's widely used in fields like submarine explorations, submarine navigations, and underwater archaeology. Although there are limitations like signal loss, the new technologies such as AI and biomimetic sonar are making it more accurate and efficient. This clearly show scientific instrumentations in physics is applied to real-world challenges and innovations.